Welcome dosto. So today we're going to revise the gravitation chapter and this one is super important for both NEET and JEE. We're going to blast through all the key concepts, the must-know formulas and yeah, even the common traps. So get your notes ready and let's jump right in.
Okay, let's kick things off with a little question. I want you to picture a cricket ball, right? It's just been hit for a massive 6 and now it's falling back to the ground. Now, picture an ISRO satellite orbiting hundreds of kilometers above us. They seem totally different, right? Well, what's the one thing that connects them? It's that single universal force, gravitation. Yep, the exact same force pulling that ball down is what's keeping that satellite perfectly in its path.
To really get a grip on gravitation, we've got to walk in the footsteps of giants. So our journey starts with the pioneers, taking us from Kepler all the way to Newton. Let's see how the laws that describe how planets move really pave the way for one of the biggest discoveries in all of science.
Now, Kepler's first law, this was a total game changer. For centuries, pretty much everyone thought that orbits had to be perfect circles. But Kepler, using some incredible data, proved that they're actually ellipses, kind of like a stretched out circle. And the sun, it's not even at the center, it's at one of the two focus points.
Okay, so the second law can sound a little tricky, but it's really all about speed. Here's what it means. A planet moves faster when it gets closer to the sun, and it slows down when it's farther away. So the big takeaway is that the speed of a planet in its orbit is not constant. This is all about the conservation of angular momentum, by the way.
And finally, we've got the third law, the law of periods. This one gives us a straight-up mathematical link between how long a planet's year is, that's its time period t, and how big its orbit is, which is the semi-major axis a. Now this relationship, t squared is proportional to a cubed, you absolutely have to know this for solving problems in your exams.
So you see, Kepler described how the planets move, but it was Newton who came along and explained why. You've probably heard the story about the falling apple. Well, he had this incredible realization that the force pulling that apple down to Earth was the very same force keeping the moon in orbit around the Earth. Just brilliant. It showed that the laws of physics are truly universal.
And all of that led to this, one of the most famous equations in all of physics. The force of gravity, F, equals the universal gravitational constant, G, times the product of the two masses, m1 and m2, all divided by the square of the distance r between their centers. This formula right here is the heart of the entire chapter.
All right, now that we've got the universal formula down, let's bring things back to Earth. We're going to explore its most direct consequence, the acceleration due to gravity, or as we all know it, little g. But, as you're about to find out, this value isn't quite as constant as you might think.
So we all learn in school that g is about 9.8 meters per second squared. But here's a critical question, especially for NEET and JEE. Does that value stay the same if you, say, climb a mountain or go deep down into a mine? And the answer to that is a definite no.
Okay, pay close attention to this slide, because this comparison is key. To find g at some height h, we use the formula g times 1 minus 2h over re. But, and this is a big but, be careful, this is just an approximation, and it only works for small heights. That's a classic trap in exam questions. Now, for depth d, the formula is g times 1 minus d over re, and this one is exact. Notice that in both cases, g gets smaller.
So the most important point to remember from all this is simple. The value of g is at its maximum right on the surface of the Earth. It doesn't matter if you go up into the sky or down towards the center, the value of g is always going to decrease. Inside the Earth, it drops off in a straight line, and outside it follows that inverse square curve.
Okay, let's switch gears and talk about energy. How much work does it actually take to fight against gravity? And what's the absolute minimum speed you need to give a rocket so that it just never comes back? This section is all about connecting gravity to energy and the incredible science of space exploration.
The formula for gravitational potential energy is V equals minus G mm over R. Now, I really want you to focus on that negative sign. It's not a typo, okay? It's there for a very important reason. It tells us that the gravitational force is attractive. It means the system is bound. You actually have to do work to pull the masses apart.
So let's put this into a real-world context. Think about ISRO launching a mission like Chandrayaan. They have to give that rocket enough speed to completely overcome Earth's gravitational pull. That minimum speed, the one you need to just break free and travel out to infinity. That's what we call escape velocity. So, what do you think that number is?
The magic number is an incredible 11.2 kilometers per second. I mean, just to put that into perspective, that's like traveling from Delhi to Mumbai in less than 2 minutes. And here's the really mind-bending part. That speed is exactly the same whether you're launching a tiny satellite or a giant GSLV rocket. It's completely independent of the mass of the object you're launching.
All right, so we know how to escape the Earth, but what if we want to stick around? That brings us to our final topic, the motion of satellites. How do they manage to stay in that perfect orbit, and what's going on with their energy?
For a satellite to stay in a nice, stable, circular orbit, it needs a very specific speed. We call it orbital velocity. You see, at this exact speed, the pull of gravity provides a perfect amount of centripetal force to keep it moving in a circle. It's a delicate balance. Go any faster, and it flies off into space. Any slower, and it falls back down to Earth.
And hey, if we look at the total energy of an orbiting satellite, which is its kinetic energy plus its potential energy, we find once again that the total energy is negative. This just confirms what we talked about earlier. A negative total energy means the system is bound. That satellite is gravitationally trapped by the Earth.
All right, we've covered a ton of ground. But now we're at the most important part for your last-minute revision. So get ready to take a screenshot because here it is, the ultimate cheat sheet with every single must-know formula from this chapter. Okay, let's lock these in. The force of gravity, F equals G m1 m2 over r squared. Easy. Next, G at the surface. G equals gm over r squared. Now the variations. At a small height h, remember that approximation, g times 1 minus 2h over r. And at depth d, it's g times 1 minus d over r. Escape velocity, always remember the root 2. Ve equals the square root of 2gm over r. Orbital velocity is almost the same, just without the 2. Vo equals the square root of gm over r. And finally, total energy in orbit, which is always negative. E equals minus g mm over 2r. Ye formulas bilkul yad rakhna.
And let's end this explainer with one final thought to chew on. We've just spent all this time talking about gravity as a force that pulls everything together, right? So, if that's true, why are all the distant galaxies moving away from us? Why is the universe expanding? Now that's a question that takes us way beyond Newton, into the really cool stuff like dark energy and modern cosmology.
I really hope this rapid revision was helpful for you. अगर ये explainer पसंद आया, तो please hit that like button, share it with your friends, and for more quick revision guides just like this, make sure you subscribe. All the very best for your exams.